Swayam Prabha. Digital India. Educated India.
Welcome. We are continuing our discussions on fundamentals of parallel computing in the parallel algorithms lecture. That's what we are continuing today in the course of high performance computing for scientists and engineers. And we have been discussing the preliminaries that we need to know before looking into the methodologies to design a parallel algorithm. And we are still we discussed some of the important aspects of these preliminary concepts using including granularity, concurrency, critical path length, task graphs, etc. We will look into few other aspects there and then start discussing on the subsequent concepts, which are decomposition and load balancing, overheads and its containment, and parallel algorithm models and Foster's design methodology. Well, so we have discussed about task we have discussed about task dependency and drawing task dependency graphs, and observed that we need to find out how many tasks can run concurrently in a parallel system, and while also noting down the fact that a particular job can be broken down into many tasks and a task dependency graph can be drawn, and this process, that generating a task dependency graph for one particular job, can be done in several ways, and we need to find out one particular task dependency graph which will give us better parallel performance. And for that, identifying the concurrency, especially the average concurrency of the task dependency graphs, and which one has the best average concurrency, that will give us a better parallel algorithm. That decision has to be taken. The degree of concurrency means how many processes can run in parallel. So the task dependency graphs, which gives on an average more number of processors can be active to solve the problem, gives us a better parallel algorithm. That's what we have seen. Now the dependency of the tasks means one task's output is required for the other task's input mostly. There is another important thing called task dependency graph, task interaction graph, I am sorry. The task dependency graph involving concurrency and granularity does not consider one particular aspect, that is, there is also requirement of data sharing and communication across tasks. So we need to do another thing, which is a task interaction graph, which identifies that which of the tasks have some sharing of data. Sharing of data is important in couple of sense. If we are in a shared memory machine, it is the same address space in which both the tasks are pointing to. There has to be cache coherency, and some protocols for cache coherency can introduce some latency in that process. There can be false sharing, which will also introduce latency there, and for a distributed memory system, if there is sharing data, some data has to be shared from one processor to other processor, some data has to be physically passed through the interconnectors from one processor to another processor, which will also put certain overhead in the calculations. Therefore, this task interaction graph is important to identify or estimate how much overhead is going to happen for one particular task dependency graph. If we look into the task or look into the decomposition and see the task interaction graph and how much data is shared across different processors, if we try to find out, that will give us some estimate on the overhead. And we have seen a sparse matrix vector multiplication example, which we have given in last discussion, that each row is multiplying with the vector and generating one product in the right hand side vector. And we can see that, say, for the task 0, which is for the first row, it is operating on the data belonging to first 0th column, first column, 4th column and 8th column. Now this 0th column data is also present in the therefore, when multiplying this, it is multiplying with the first 0th element of B vector, first element of B vector, 4th element of B vector and 8th element of B vector. Now this 0th element of B vector is also multiplied with task 1's, that is the column 1, row 1, task 4 row 4 and task 8 row 8. So the same data each of the 4 tasks are accessing. Therefore, task 0 has interaction with task 1, 4 and 8. So, and that is how we can get a task interaction graph and take a decision that which tasks are interacting with each other in terms of data. In case of a shared memory system, they are trying to access the same data, there can be contention, there can be cache coherency protocol, there can be false sharing and overhead. In terms of distributed memory system, a same copy of this data, or in some sense here it will not happen probably, but in some cases a similar copy of some of the data has to be transferred from one processor to other processor. Therefore, it is also important to look into task interaction graph to identify the overheads in parallel program. And now once we have we got all the tasks and review the task dependency graph, we need to map the tasks to the processors and see that which processors will run during the execution and which task will go to which of the processor. So, for example, here we can see that the previous class example, that the finding out a school which is based on which is a particular medium of instruction, which has a fee, annual fee less than certain amount and belongs to one particular board from a list of 10 boards, and this was the task dependency graph for that. And now once we have identified the tasks in previous class example, now mapping means each of the tasks has to be mapped to one particular processor, and some of the tasks will be mapped, some of the processors will be still active once the first set is done, because there will be further tasks. Initially there are 4 tasks, now there are 2 tasks, so 2 processors will be in dormant state and 2 will be active, and finally there is only 1 task, so 3 processors are not doing anything and only 1 is active. Therefore, the other processors are going into a latent stage here. So, even we are using 4 processors, we are not getting speed in terms of speed up of the factor of 4, because many processors are going into the latent state. And also it is important, in the second part we can see similarly that the processors are working like that. And another thing, these are not, we will not call them as processors, we will call them processes, that this process is working and taking care of the task. Why, I will come in a moment. And the maximum amount of data that should retain to one process, that will be another idea of mapping, that you will avoid data transfer across the processes, so that one process which is active from start to end, it should have maximum amount of data. That is also another important concept here. And we call what is running in concurrently and in each of the processing the task, that running instance, we call it to be process, and processors are the hardwares which is executing process. So, in many cases processors and processes are equivalent, only process is the programming thing, that there are multiple processes which are taking care of multiple parts of concurrent parts of the program, and processors are the hardware which are executing the processes. They can be same in many cases, but it is also useful not to mix up between processor and processes, because there can be hybrid parallelization, where one process takes care of certain task and there are co-processors in which this task is divided. So, processor and process may be of may make wrong confusion if we mix them up. For more technically, we should use the term process, which is in which the tasks will be mapped. So, one of the important part is mapping, that each of the tasks will be mapped to a process. Now, we need to see how the task can be decomposed, how the main job can be decomposed into many tasks. We have earlier discussed about decomposition, that given a large job, it has to be decomposed into many tasks. and we have seen some of the methods of some of the decompositions in our for matrix vector multiplication or this search problem, given two examples of decompositions. But what are the ways? And there are 5 different standard methods of decomposition. One is called a recursive decomposition, the next one is data decomposition. These two will study in detail. The third one is known as exploratory decomposition. So I will not spend much time because it is not very much of very high use in scientific computing, but in a sense you need to find out solution of one problem, and instead of, and you are not sure about the right way of solving it. So instead of solving it sequentially, you have to make few trial and error, and each trial case you give to different processors, make different tasks for each trial case. And this decomposition, it's a trial error based solution, and each trial is being a task, is a exploratory decomposition. There can be speculative decomposition, that for example for chess playing, after one in our childhood it used to be a story that a supercomputer has beaten Garry Kasparov. So how did it work? So when Kasparov is giving one move, the supercomputer is calculating that what are the branches of this move, what are the next possible moves, and what will be the solution for it. So speculatively you calculate what are the, find out the next moves and find out the next solutions, and once he gives the next move, it is already computed by that, and there is mix up of that. So we will not spend much time on exploratory and speculative decomposition, but let us go to recursive decomposition. Recursive decomposition is also called divide and conquer strategy. A big problem is there, it is broken down into small problems, and these small problems are further broken down into small problems, and finally it is a very small problem which goes to each of the computer and it can solve it quickly. For example, you have to do a sorting of a set of 12 numbers. So first identify the numbers which are less than 5 and identify the numbers which are greater than 4 and make 2 sorts, and then identify the numbers. So you get 1, 2, 3, 4 here which is less than 3, identify the numbers which are greater than 2 and get 2 of the parts, and then again break it into find out the 1 and 2 and 3 and 4 there. So as we branch this decomposition, finally we end up in a process where, see, these 2 processes can run concurrently, these 4 processes can run concurrently, again these 4 processes can run concurrently, these 2 processes can run concurrently. We break them into many concurrent processes and do a recursion of that. As we break down the job into smaller tasks, we get more concurrent processes, and we get a simpler problem in each of the processors which can be solved fast. And through this, finally we have conquered the space. After a simple algorithm is the breakdown this less than this half like thing is executed, we get many concurrent jobs, and finally each processor is coming out with the solutions. So this is a recursive decomposition. But for scientific computing, we are more interested in data decomposition. That is, we divide the job by the data, by what is going to happen in the data. For example, while doing a matrix vector multiplication, we can partition the output data and say 2 matrix multiplication. Each of the matrix is considered as a block matrix, and the output is a matrix of this four block matrices, and each process is calculating one of the block matrix. So the output, the actual task is decomposed into many subtasks by partitioning the output data. That first task computes C11, second task computes C12, third task computes C21, fourth task computes C22. This is partitioning based on the output data. Each process computes one partition of the output data, that is done here. However, there is one particular issue, that is say both C11 and C12 is operating on same data A11. So there is huge amount of task interaction which is possible. Now there can be also input data based partitioning. Say I have to do a numerical integration, find out fx dx within a range, and I distribute, and this is the fx function in x axis. I distribute x1 to x2 the range into many n small partitions. Each partition is of with delta x. So, the summation is the integration is summation of fx into delta x over the partitions, and then I divide the summation into multiple, it is like the sine series, into multiple tasks. Task 1, which goes to processor 0, takes care of the first summation, and the summation in this task is its summation over the, for task 0 it is a summation over these 4 zones, and finally task 2, task 3, task 4, task 5, many tasks are there, and each task is taking care of the small amount of data given to it. So, we are dividing the input data, partitioning, making partitioning, divide the getting the tasks, generating the task set depending on decomposition of the input data, which is what is the sum, and the final value input data is what are the input points, and the final value is sum of the all points. Well, the tasks are designed to concurrently operate on the partitions of input data. Then, and both input and output data based decomposition follows owner partition rule, that the amount of data given to one particular process, it will do all the computation for that amount of data. If it is input data, it will do all the computations involving that input. If it is output data, it will do all the computations to get that output, and it is called the owner partition rule. Decomposition is also possible by partitioning both input and output data. Say we take up a matrix vector multiplication, and first block of rows with first block of column gives one block of the product matrix. First block of row with second block of column gives second block of the product matrix. Here we are partitioning it based on the output, as well as making partitions based on the partitions on the input also. So, it is partitioning both input and output data. There can be partitioning on the intermediate data, because in both the previous cases they are sharing lot of data. There is huge amount of data sharing, and which will give huge overhead. Instead of that, we take the make intermediate matrices. So, instead of writing A into B is equal to C, we take first block of rows of A, columns of A, and first block of rows of B, and get a intermediate matrix D11. Similarly, we get a intermediate matrix D2 by second block of columns of A and second block of rows of B, and then sum them up. So, this is getting two intermediate, creating an intermediate data and partitioning the main matrix into these two intermediate data set, which reduces the data sharing across the processes. Now, it is important that mapping is important, so the tasks are mapped to different processes. Say we think of and where the important part becomes load balancing. We have earlier seen that all the processes are not active. Initially for the search problem, 4 processes are active, then 2 will be active, then 1 will be active. So, some processes are less active, some are more. Which one is less active is sitting idle, and therefore, we are not getting write speed. So, in case if we try to map the job from tasks to processes, and some of the tasks are less heavy than some other, the less heavy task processes will finish their job faster and will sit idle, and therefore, we need to do a load balancing, that each one is getting almost similar amount of load. So, if we have a sparse matrix vector multiplication, and these are the non-zero elements of the matrix, and these are the zero elements of the matrix, and now we do a decomposition in which each of the block is given to different processor, different block is given to different processor. We can see that the processes which takes care of these blocks, this sparse matrix vector, so these elements are 0, they are practically working with zeros, therefore, they do not have to do anything. 0 multiplied by 0 is anything, 0, we know the number, we know the result only, we will not ask the processors to work there. So, this will be load imbalancing and less work for the processors as the numbers are 0, and while others are working, they are still sitting idle. Instead, we could have given some amount of work to these processes in computing the non-zero part of the matrix. This would have been a better load balancing. So, the actual work will be in reality, not in practice, not by assignment wise, but in practice given to the all the processors, and each processor will can finish their job faster compared to the case that some processors have done already fast processes already in a faster time, but others are waiting, that others are still working, that would not have happened. So, load balancing is also important when writing a parallel program, and it is usually programmer's duty to tell which task will go to which process. So, he has to do a mapping, he has to map the process tasks into the process, he has to map the tasks into the process, so that load balancing is taken care of. And this mapping is there are two classes of mapping. One is static mapping, where mapping is done beginning of the calculations and it is fixed, it does not change throughout the computing. So, initially this some of the tasks are identified and this task will go to this process, this task will go to this process, this is fixed. And say we do a data partitioning, so we can do block distribution, that means these are the, so we do a matrix vector multiplication and do it based on the output data. So, these are the different tasks for which calculates different parts of this data, and each of these tasks goes to one particular process, and that task means our task takes care of one block of the output data, and each task goes to one part of the matrix. Sorry, each task goes to one particular processor, that is called a block distribution. A block by block we distribute the tasks. There can be different type of block distribution also, right? Based on both output input data, what we that decomposition, here also you can do block distribution. So, sequentially 1 to 16 or sequentially here 1 2 3 4 up to 15 jobs are given to different processes. Now, there can be block cyclic distribution, where instead of, so what is the well, instead of giving the jobs 1 to 16, you give first 1 2 3 4 and then again you repeat a cycle of that 0 1 2 3, again 0 1 2 3, here you do 0 0 1 0 1 2 3 2 3 0 1 0 1 2 3 2 3. So, you make a cycling of block distribution. What is the advantage? That there will be some of the cache coherency related issues where some read write protocols are there, some processors are not working, or some message transfer issues, some processors are not working, whether others are working to take care of the communication or data sharing issues. And then you can do a read write read black algorithm, that this processor is working, this one is working, but these two blocks are not working because they map to same process. Instead, these two blocks are working, or say these two blocks are working, so that they do not have cache overhead related issues. So, block cyclic distribution is good in some cases to reduce cache overhead. And there can be randomized distribution for cache over also, that is then there can be graph partitioning. Like all these are not matrix vector type of products, when you know right number of rows and right number of columns and get very uniform number of blocks and distribute the job. There can be cases, for example, finite element based simulation on Lec superior, which is again taken from Gupta's book, that it is the number of tasks and each small triangle represent one task, say here, which is computation on that particular element in the Lec superior domain. So, each task has different size and the tasks are very non-uniformly unstructuredly distributed over the geometry. One idea is taking some of that we know that this will be distributed among 8 processes. So, generating random numbers and allocating within 1 to 8 and finding out which will be the allocation. So, it is a random way of distributing the job. The problem is that there can be different part of the domain given to different processes, and there can be huge data sharing requirement, because the neighboring job goes to different process. Instead of localizing the data, we are randomly distributing the processes, so the data is less localized and more sharing is required. The other one is a graph partitioning, in which more localized job distribution is possible, and the graph partitioning is better. And these two are randomized and graph partitionings are the techniques of task distribution, especially for Laplace equation type of solvers, when you have a very irregular domain and you have unstructured distribution of mesh points. If you have a structured distribution of mesh points like matrix vector multiplication, or like working in a Cartesian geometry or polar geometry, the block or the cyclic methods are better. And there can be dynamic mapping also, that the computing is completely changing during the scenario. Say we are solving about molecular dynamics simulation, and the number of molecules interacting with each other, their distribution, etc. changing, solving some chemistry equation, the chemistry problem, the composition is changing. In that particular case, instead of static mapping, it might be of importance that dynamically the mapping is done at different stage of calculation. As the arrangement has been changed, the problem configuration, problem size, everything has been changed, it might be important to do a dynamic mapping. There can be cases where the geometry itself is changing, the topology is changing, and therefore you need to do dynamic mapping. This can be done by centralized schemes, that there are self-scheduling programs using master slave. So, one computer is asked, or one process is asked to be a master, and it will see that what is the total amount job at each different instance of calculation. It will do a new task partitioning and assign different new decomposition and assign different tasks to different processors. And there can be distributed schemes where there is multiple zone, is like a recursive type of distribution scheme is given to it. Multiple processors are again breaking down and giving their jobs to other processors. So, next important part is that, because we understand that when computers will work in parallel, all of them are not working in together, some are going to be idle, and as well as there will be communication requirement across the processors. So, the next important part will be understanding the overheads in parallel program, and the sources of overhead and performance degradation are load imbalance, that the some of the processors are getting more work, some are getting less work, and communication overhead. These two are the communication overhead, means when there is a need of data transfer across the processes. Now, in order to reduce the overhead, one important step is doing an efficient mapping where load is balanced. These are also very important steps for a parallel programmer, that he knows what are the overheads and how to reduce it. Maximizing the data locality, that in compared to randomized and graph partition decomposition. In randomized, the processes are one particular processes has tasks spread across entire domain of the given task set, given job set, but in graph partition case it was much more localized. So, if we can increase the data locality, the data sharing or message passing will be reduced, and there will be also not much need to share data with the process which is at far end of the node. It will only share data with the neighboring processors. So, the data sharing time will be less and overhead will be less. Minimizing the volume of data share. So, one is that data locality will minimize the requirement of data sharing, but again when data has to be shared, some way the volume of the data exchange has to be minimized, and the frequency of the interactions, frequency of data sharing, that has to be also reduced. Once data is shared, it will be shared as a packet, because every time a data sharing will take some startup time. So, as many times data sharing is happening, more startup time is included and more overhead is increasing. Minimizing the contentions by process mapping, that is like a block cyclic mapping. Not all the processes are trying to read from the same location of the data, and contention is there, reducing that, and reducing communication latency by overlapping communication with computations or other communication. When computation is costly, so when one processor is computing, it has some overlap. When one processor is communicating, that time data has gone from this processor, tries to reach another processor. At that time also this processor goes for some other work. So there is some non-blockingness during communication, that it doesn't goes into halt because it has sent the data to somebody else. While it has sent the data to somebody else, some other task has been picked up by the process and it is working, and that also reduces the overhead. Well, so we have seen some of the issues regarding the parallel algorithm and the points on which a programmer has to take care. That involves doing a right decomposition, then mapping it accordingly, and then looking into the overheads so that the communication time can be minimized, and even the communication time cannot be minimized by a communication computation or communication overlap. Some of the communication time can be utilized by the processor itself. Now in the next class we will look into that, using these concepts, how a good parallel algorithm model can be developed and what are the available parallel algorithm models, and we will take some examples and see how these models can be implemented to parallelize that particular example problems. Thanks.